This is our interview with Professor Roald Hoffmann for the Argentinian meeting on Catálisis and also a conference of Catálisis for the Mercosur. So thank you, Roald, to be here with us and try to chat a little about quantum chemistry and in particular what is important or useful for catalysis people. You know, our audience here is mainly from experimental people doing a lot of experiments using chromatograph. So we need to convince that people that computational chemistry is useful. So what do you think about the role of computational chemistry in surface science and catalytic reaction, or what the people from Catálisis receive from theoretical tools?
I really am not the best person for your purpose, of the purpose being to say something to the Catalyst meeting. It's because, as you know, I have not worked in the last 15 years or so on catalysts or on surfaces. I retain an intellectual interest, but it is, I'm a little out of the field by now. So first of all, Alfredo, I'm very happy to talk to my friends in Argentina and in the Mercosur community about anything, and about catalysis in particular. Of course, I don't have to tell people why catalysis is important. What we get from nature, from natural products, is just fine. But everything in the world begins from nature, and it is human beings who transform it into something of use to us. And we should worry about whether the transformations benefit nature around us and ourselves. But transform we must. We have been put on this earth to change things. And you know, catalysis is really, to me, the best example in the world of human beings making for effective change, for economic and now ecologically consistent change of things into something of use to us and of use to the world. So I think very well of people in this community, of the people who, through the work of their hands and minds combined, come up with new ways of transforming matter. And now I'm a theoretician, and you ask a question about the possible role or the role of theoretical chemistry and computers in this enterprise of catalysis. In the end, the enterprise catalysis, or chemical manufacturing in general, is of course experimental, and it is on a scale of transformation which is far beyond what we see in an academic laboratory. To see vessels with 5,000 liters of something being changed into something else is marvelous and interesting. It used to be that you could try the next molecule off the shelf as a catalyst. Perhaps you had some leads for what might be an effective catalyst. You saw that rhodium was very good for affecting a change where a nitrogen oxide was transformed in some way into nitrogen and oxygen. So you might look for rhodium, and of course you look for this intelligently, and the rhodium is very expensive, so you would look at to see if perhaps cobalt above it in a periodic table would serve. And there is a reason for the periodic table, to try it. It gives us intelligent ways of trying. With time and with so many chemists trying things, it's not sure that everything has been tried. After all, chemists have made 70 million new molecules that they've added in 200 years of frenetic activity to what nature has given to us. And not every one of them has been tried as a catalyst, not even every transition metal complex, if you limit yourself to metals being effective in catalysis. So not everything has been tried, but one wants to be a little bit more systematic. And the kind of Edisonian way of trying the next molecule off the shelf has its limits. It's just very ineffectual to do that, though it's still done to a certain extent. But even then, it is done both in a catalysis industry and in the pharmaceutical industry in a kind of directed random searching. So you find a lead, a molecule that is effective as a pharmacological drug, or you find a rhodium salt or a cobalt salt that may be effective as a catalyst. And of course you try things around it, but even then there is a semi-infinity of ligands to attach to that metal atom. So one wants to do it somewhat intelligently. And doing it intelligently means finding out how that catalytic process works actually. What are the basic steps in it? And what are the effects of the various substituents in the organic or inorganic molecule that will make this an effective catalyst? And again, one can do this to some extent in random, and one can do this using simple ideas of physical organic or physical chemistry, substituent effects, things like that. But you could also use theory to help you do it. It's not only that you can also use, I think, if you are really in the business of trying to find something new, something that improves the yield of the reaction, something that gets you out of a catalyst that goes sour, that goes ineffectual after 2 weeks of use. You need to know the mechanism of the reaction, and you can today use theoretical chemistry very effectively to accomplish this. It is not foolproof, and you must not believe the propaganda of my theoretical chemistry colleagues. They are trying to sell you, and not only them, but the people who sell you the modeling software for materials or for pharmacology. Of course they are selling things, and scientists are just as bad at selling things as the people who do advertising. So you must learn as a consumer to take everything with a grain of salt, but you just can see that you can optimize a catalyst, or perhaps look for an entirely new one using quantum mechanical methods. I think it's part of our times.
So, if I understand, it is impossible to replace inorganic chemistry or the knowledge in the lab just by a computer and a good software. You always need to know something about the reaction, to combine theory and experiments and knowledge and a lot of things. It's not always possible to predict just using a computer.
Yes.
That's your idea.
Yes, I think if I were designing a modern chemical laboratory in some new industry, I would, aside from building in a structure in a laboratory which enhances interaction. What I mean by that is I would build in an Italian espresso bar on every floor in that laboratory so that people can go and talk to each other. But aside from that, I would build a group consisting of some well-experienced catalytic chemists who know something of what works and what doesn't. And then I would build in a group of organic and inorganic chemists who study the reaction mechanisms, who can study experimentally using physical chemistry the kinetics, the rates of the reactions, how a catalyst changed them. And I would build in from the beginning a theoretical group that could model those reactions. I think a modern approach to catalytic chemistry in an industrial world must involve these three components.
Well, what about the skills that the people need to understand or to apply computational calculation to any catalytic? It is necessary to be a sophisticated theoretician, or you can do something knowing something about the programs or cooperate with some experts. What do you think is a basic recipe to start doing theoretical calculation, or helping or working together,
Yes.
maybe?
So one of the remarkable things of this world is you don't have to understand everything in order to do something with it. The person who drives a fire engine to a fire really does not need to understand the workings of the internal combustion engine that drives him there. But he should understand something about the physics of either pumping water and up to what level you can pump it, or how to extend the ladder. I think one has to know something, but one can accomplish a good bit with partial knowledge, always aware of one's limitations. In that ideal computational group in the new company I'm setting up here, I would hire something like a group of 5 people, computational chemistry, and this is in a laboratory which I think might have, I imagine, 50 or so PhD level people. And among those 5, there should be one who is really the person to go to when you can ask the question of what is the most reliable method for this kind of a problem. And the others could be people who have some idea of the limitations, but who would bridge over to the real chemists who come and bring them the problems. Anyway, I think it's possible to do something with substantial partial knowledge, but it is hard for me to imagine, for instance, that a working member of that computational chemistry for catalysis group, I've just invented an acronym, it's called C-cubed, Computational Chemistry for Catalysis. In that C-cubed group, it's impossible to imagine that you could work with a technician as such. You would need someone with at least a master's, if not a PhD level, to do the calculations.
Okay, well, maybe you remember some example or some predictions that theory brings to chemistry. I remember your own rules, the Roald Hoffmann rules in organic chemistry. That is working. Your predictions are okay. But you know some example of prediction that never works or gives unreal propositions? Or
Well,
do you remember someone?
Yes, there are many. So one of the fortunate things about doing theoretical chemistry is your predictions have to be right only about 37% of the time. And the 63% of the time they are not right, people forget about. So I have predicted molecules that have not been made, but I've been fortunate enough, whether they're metallo-aromatic compounds or in the Woodward Hoffmann rules, to be able to predict things that work. Some things do not work because we have not yet found the methods for doing this, for doing the transformations. I will give you an example. I used to think that of those molecules with the formula of 1 carbon and 1 hydrogen, that is CH, that benzene, C6H6, or a molecular crystal or a liquid or of benzene, that this was certainly the most stable arrangement of the 1 carbon and 1 hydrogen taken as many times as you want in the world. Until a few years ago, I did a calculation on graphene. So graphene, everyone in the world knows what graphene is like. So graphene is a network, it's one sheet of the graphite lattice, a network of carbon atoms. Graphene is where every carbon of that graphene network is saturated. And this is accomplished by taking a graphene net and then adding from the top 1 hydrogen at every second carbon in the 6-membered rings, and from the bottom. You cannot add 6 hydrogens from the top. You'll get terrible strain. But if you add 3 in each 6-membered ring, 3 from the top and 3 from the bottom, you have graphene. Graphene has been made in not very ordered forms. It turns out that graphene is thermodynamically more stable in calculations. No one has measured the heat of formation of the poorly formed graphene that has been made. But in calculations, it is about 9/10 of an EV, that's about 20 kilocalories, per C6H6 ring, that graphene is more stable than benzene. I didn't believe it when I saw it. I didn't believe it when I saw it in the paper, and I had to do the calculation myself. I still didn't believe it when my student brought me the calculation, but we did the calculation with better and better methods, and it's not only us, and I'm sure that graphene, when it is made reproducibly, will be found to be thermodynamically, thermochemically, have a lower heat of formation than benzene per CH. So what's the problem with it? Well, there's a big entropy factor against the making. If you think about benzene molecules coming together, you can actually reason out that from the point of view of bond energies, it's downhill to graphene, but from the point of view of the entropy of assembling the benzenes and making them stay in place, there's a big barrier to doing it. I'm sorry I went on at some length. I wanted to give you an example of something that we predicted, and others too, that has not yet been realized. There are many examples. The literature is just full of predictions of molecules that people say they are stable, and they really want to say that they are stable in a bottle, what I would call either bottleable, which is a bad English word, or bench stable, that they are stable under the conditions of a laboratory. And yet those molecules have no chance of existence, no chance at all. They will very quickly react with each other, and the theoreticians could prove this. This is why in my hypothetical laboratory, I want there to be, in addition to those 5 chemists, 10 experimental chemists who can tell the theoreticians, you're crazy. That's not going to work. Now, maybe it's still worth trying. It's okay. It's from that interplay, which is going to happen at that Italian espresso bar that I mentioned on each floor. That interplay is what is going to lead to something new.
Well, you mentioned many times about the role of intuition in chemistry. What is, you still believe that intuition is quite important to be a good chemist, to have this expectation about the reaction and then do the experiments and then do the calculations? How important is intuition?
It's very important, especially important, as you're going to realize in a few years. It's especially important for older people because it's the only thing we have that gives us an advantage over all those young kids. They are quicker. I've looked in my notebooks from the university and I solved problems set by the professor. I solved problems that I could not dream of solving right now. They were in a certain format. They were in a school format. So as I get older, the advantage I have, I'm getting, like all older people, there is some short-term loss of memory, but I have somewhere in there a feeling, I don't know what it is, it's some burned-in neural pathways, so that an idea comes and a connection is made to some other ideas. And you know, if you asked me, I could not tell you why I made that connection, but I had an intuition. So where does it come? It comes from previous experience. It is not wasted. It is not necessarily wisdom. And sometimes your intuition can lead you astray. So the thing that I recommend for, I do think intuition is important. What I recommend for my theoretical students is use your knowledge and intuition when you do a calculation on something. Try to predict before you do the calculation with the world's best computer program. Try to predict what qualitatively the outcome of the calculation will be. Will the carbon monoxide stand up or will it lie down on that surface? You will never be able to predict by how much it prefers. Is it 5 kilocalories or 7? Nor would you trust the computer program to give it that to you. But the qualitative prediction is a test of your understanding, which is knowing what the physical factors that go into making an observable and sort of making an order without thinking, making an order of magnitude estimate of the contribution of the different things that make something come out. And so you do this qualitative prediction. Then you do the calculation. And if the calculation confirms your qualitative notion, maybe giving you a more accurate number, then that's very good. You must not sit back and smile. You just take it that you have provisionally a good understanding of the situation. And the computer is then being used as the slave that it must be to give you the numbers. If the computer gives you something which is against your approximation, then you have an interesting choice, an interesting existential moment. And that is, either the computer is wrong, and you could have put in garbage and you got out garbage, but it could be the computer doesn't have the right approximations built into the model, into the program. Or it could be that the computer is right. So there is, if you make the second assumption, it all depends on how strong your intuition is in the result. Of course, if you think the computer is wrong, you should repeat it with another program if you get an unusual result, or ask someone else to do it. But supposing the computer is right and your intuition was wrong, and your initial approximate estimate of what it should come out is wrong, then you have an opportunity to teach yourself. So what you must do is re-examine your assumptions in your model, in your conceptual model, which did not involve numerical calculations, and try to find a reason why the computer gave you the result. And if you do that, I found from my experience, before long, you can see, you feel like you should kick yourself in the behind because you were stupid enough not to see what you should have seen right away. And what has happened then is you have learned something. So this is what I'm describing is an ideal world where we learn something from computers. And the next time you're going to make the right prediction on this and your understanding is gained.
Roald, so many people who don't believe a lot in quantum chemistry always said, okay, you are doing a very nice calculation, beautiful pictures or models, but you are still working at 0 Kelvin at very low pressure. How do you feel this pressure gap comparing with industrial conditions, for example? Which is the way to be ready to model in real conditions? It is possible, or would be possible?
It's becoming possible to model it. It's the approaches can be done. There are several approaches. One is to do dynamics, so you study trajectories of molecules impacting with the surface, colliding with each other in solution, and you have to invent then. This is not what I have done, and I don't know how to do it, but what you have to invent is measures for looking at those dynamic calculations, ways of thinking about them would give you insight. For instance, just to be specific, if you're doing something in a liquid or gas phase, there is a measure, there are various correlation functions, radial correlation functions, which tell you if you average over hundreds of thousands of trajectories, if you have an atom at this point of space, then the other atom is at some other point of space. These radial distribution functions and correlations will become the tools of the dynamics community. The dynamics community can dial in a temperature. I think they can dial in a pressure too. So I think the gap will be bridged. I think getting the total stoic, the mess of compounds that in any realistic reaction is there interacting with a heterogeneous surface, that's going to be difficult. But I think approaches to this can be made. They are very computer intensive, so one had better have a good budget for that laboratory.
When I was thinking with Daniel Damiani, one of the organizers of this Congress in Catálisis, we was rereading one of your papers in Chemical Engineering News in 1974. So many years ago, I remember the paper is called Theory in Chemistry. So can you tell us briefly how the world of theoretical chemistry changed since that days? It changed a lot, of course, but...
Yes, it has changed a lot, and it has impacted chemistry greatly. Computers have, of course. That is the major change in our lives, is cell phones and computers. That's how my office looks different from how it looked when you and Graciela visited. The computations have become much easier. The extent to which we could worry about whether they're reliable has also become greater. So before, we just didn't worry when we did an extended Hickel calculation. And now we worry, and I cannot any longer publish an extended Hickel calculation. So how have I survived? I've done the better calculations, but I've figured out ways to get similar qualitative explanations out of them. So something that has not changed, and something I may have written about there because I could see it coming, is that there is a difference between calculating something, simulating something, and understanding it, explaining it. This is really a philosophical question at some point. It has to do with how we know things, epistemology. It's not a question peculiar to chemistry. In every field of the social sciences especially, take economics. What we have today is simulation and modeling. And that's not just the weather, where thank God it works much better, but it is also, but an interesting thing with respect to where you are is this year there is a controversy about monitoring El Nino, the currents in the Pacific that are needed to bring rain to California, to our California, but which will influence South America as well. There is modeling and simulation, and they have improved, but there is a twofold danger in paying too much attention to the calculations and the simulation. The thing is that I think you want to have understanding, and the understanding to me is knowing the mix of different physical observables that go into making, of different physical mechanisms that go into making something, knowing the magnitude of each roughly. To me, an explanation is something that's done with pencil and paper, and I still use a fountain pen and pencil, and is done qualitatively. It's done in a teaching mode of me talking to my research group at a research group meeting, saying, I understand why this group of atoms is bent. It's qualitative inherently. So I think that with the emphasis on calculations, there has been a shift away from explaining and understanding qualitatively. You know where it still takes place is in a teaching situation. So if you look in the lectures that people give, whether it's inorganic chemistry or surface science or organic chemistry at the university level, thank God the student does not have a plug in the back of their neck like in Matrix, and so that they get, I say thank God that they're not there, that they're not plugged in. The professor and the student are still engaged in some dialogue which involves words and pictures. It may involve equations, chemistry often formulas. They are not immersed in a virtual reality, but they're communicating, and the explanation is given to the students in some simple terms. And you know, I see a curious thing in some scientific papers which involve chemical theory, that there are the world's best calculations presented to get a certain result. But then when it comes to discussing that result, they go back to the teaching situation that was in the university course, and they use orbitals and frontier orbital arguments in my context, so that they use a simple world to explain. And to me, what that is telling me is the explanation lies at that simple level. The second problem with simulations and computation is that it's the sort of the computer programmer's mentality that when you have slaved a long time to get a program right for a model for something, complicated model of many chemical reactions going on at the same time, which is what a chemical engineer might model in a reactor. And when you have gone to the effort of doing that and gotten every last bug out of the program, and the program works, then it's hard for you to believe, with the immense amount of effort that you have put into that program, that anyone could explain the result qualitatively and simply. And yet one can. So there's something about the psychology of the computer programmer which argues against that person or the person who accepts the simulation to ever believing that there is a simple explanation. I think they're wrong.
Okay, Roald. Yes, we was talking about this new field for us. It's biocatalysis and enzymatic catalysis. Maybe you can make a comment about these fields. Maybe there are many important processes working on enzymatic field. So, do you know these molecules are quite big sometimes, much bigger than carbon monoxide or something like this? But do you think we can still do something in theoretical calculation in such big molecules?
So, first of all, I don't know too much about biocatalysis. I recognize that it is an emerging field. I can see that. We had recently a new department formed at Cornell. It was called Bioengineering Science. So that was clear a recognition of the merger of biological reactions and chemical engineering, which is what it represented. Yeah, the complexity of a typical enzyme seems greater than that of, let's say, a surface of anatase or rutile, but you know, part of the feeling that the former, that the inorganic surface is simpler, part of that feeling comes from the fact of you're unwilling to put in the real complexity of that surface with all the defects and partial exposure of atoms that that surface has. So what I'm saying is the heterogeneous surface is also complicated, and maybe you haven't modeled it quite in its full complexity. Maybe that's okay, because things happen only at one place on that surface. The other thing is that engineers are very good at, you take a system, if it works, you use it, you don't worry too much about the complexity of the system. Certainly, organic chemists used to homogeneous reactions in a flask have problems looking at a bioengineered system where you generate a DNA snippet to do a certain function, you insert it into a gene of a bacterium, and then you have the bacterium manufacture the molecule for you. They look at that. That doesn't look quite like what the English would say. It doesn't look like cricket. It doesn't look like organic synthesis that they are used to, but it is a way of using the world around us to affect the transformation that you want. It doesn't matter how you do it. I think that we're going to see more of this. One of the interesting areas is to take the knowledge that we have from enzymes being able to do certain reactions is what is usually called an interesting direction, which I have some hesitations about, is bioengineering. That is, making an enzyme that is better at doing whatever the task is, whether it is putting a methyl group in a certain place in the molecule, of engineering that enzyme through laboratory evolutionary conditions, or partially with synthesis of genetic material incorporated, of engineering an enzyme that is better at doing what it's doing than the natural one, that has a little bit of hubris around it, that I'm playing God, I'm playing something better than nature. But you know, we've been breeding cattle for our own purposes, or rice or potatoes in varieties which we can use. So we have changed nature, and this is probably okay. I think it's an interesting field. I wished I knew more about it.
Well, let me just finishing one more question, and one is directed to the students who we were trying to interest in theoretical chemist. Do you can give an advice how to train better people who like theoretical chemistry? For what I understand, you will train these people in some experimental research, okay? Just to
Yes.
to know something about reality. But
Yes.
what about studying more mathematics, more physics? What do you think about this? Sometimes people from chemistry don't like a lot to study physics. You know, it's say it's too complicated, too many formulas, or it's mathematics. What do you think about this?
So in order to do theoretical chemistry, one has to know theory in chemistry, one has to know quantum mechanics, which is physics, and one has to know, to do that, one has to know underlying mathematics. And with these days, one has to know the IT world and computing and the tools of that world. In my experience, though I understand that chemists partition in some way. Usually they partition halfway through an undergraduate course. It's all a question in general of in what way people, smart people, are willing to accept complexity. And it's clear that for reasons that I don't understand, that comes in very different ways for people. But specifically for chemists, something happens around when they take a physical chemistry course, that there are some people who have no problem at all with 7 asymmetric centers in a molecule that they are trying to synthesize, an organic molecule, have no trouble with 3-O-erythro, with stereochemistry, but they have trouble with the equation like they encounter in physical chemistry. And there are the other people around who just cannot seem to accept the complexity and often the lack of certainty, so that when they are faced with making a molecule and someone says how to make a CC bond, let's try that. And if that doesn't work, there are 98 other ways to make a CC bond. And some people have trouble with the fact that there isn't one way to do this, and that's the right way. And that's how a lot of chemistry works. So people partition in that way. I accept that. I think that the reason for my success as a theoretical chemist is that I am in love with chemistry. I love molecules and I love their complexity, organic and inorganic, and I'm absolutely unafraid of any molecule in the world. I know I can understand it. In at least the structure of the molecule. Okay, so I've learned how to trust the people who give us the structures. I've learned when a crystal structure is good and when is it bad. I've learned when to believe in an NMR spectrum. But basically, I love molecules, and at the same time, I was reasonably good at the theory. So I was lucky. I came into chemistry. I was able to apply the theory to the chemistry. So I'm really a chemist hiding as a theoretical chemist. But we're back to your question. What about the education of the people? What shall we tell the young people? They're not going to be able to decide what is the best calculation to use, not going to be able to decide whether to trust the calculation or not, unless they know some quantum mechanics and at a reasonably advanced level. Overall, I would say that the problem for chemists, for scientists anyway, are drawn to science on the basis somehow of their facility with mathematics, the natural language of science. I think the problem for theoretical chemists is that they need to know more chemistry rather than that they need to be better at theory.
Well, thank you very much for your talk. And
I wish people thank you. I wish people at the conference well, and you are at the front lines trying to make better processes, trying to do things that have not been done before. It's not easy. I appreciate what you do. Thank you very much.
Okay, thank you.